All right, and so let's now look at part C of our example. And we're still not done with example 2 because my aim is I would like to have my viewers to be able to see as many examples as possible. But please keep in mind, no matter how any instructor tries, it will never be enough to cover all examples out there. So after you view the video, grab any calculus textbook and look into their problems. And I'm sure any textbook in the market out there for calculus has a section, a chapter that talks about implicit differentiation, and you will find tons of problems out there. Or get on the internet and find problems where you can find the derivative using implicit differentiation. And so I can just try to show you as many examples as I could, but I can never make that promise that I'll be able to to go over every kind of examples out there. It's students in calculus. You guys, any one of you are mature enough in math to take what I teach as example and be able to apply and see some generality and apply that generality to other problems outside of what I taught in my examples. Okay, so let's dive into another example over here. We have learned some how to find derivative on some trig function, haven't we? Okay, so in my earlier lecture, I delivered some basic understanding of taking derivative on a trig function. So let's get to it. Problem part C here gives me, how about in my creativity, how about x times cosine of y, okay, it's a trig function now, and equals y. Okay, and so now once again with that same advice I've had earlier in the earlier problem, same example here, but just part C, I had a little advice. Anytime that your equation has the variables being kind of all over like this, you can decide to bring all your variables term. See, this is a variable term, and this is another variable term. So bring all of the variable terms to one side. So I would, and it's just me, I favor the left-hand side, so I'll bring this term here to the left-hand side. So I'm going to subtract y from both sides. So in my next step, left-hand side becomes x times cosine of y minus y. What's remaining behind here on the right-hand side? It's a 0. It's another constant. Okay, and so now we are ready to take, in my next step, we are ready to take the derivative in respect to x. Again, the entire example 2 is all about taking the derivative out of the two variables. We want to take in respect to the y, take the y as a function and the x as the variable. Okay, and so that means if this is an equation, then we can do the same equally on the right hand side as well. So let's now take care of the easier side. This derivative is a constant and it's a 0. So the derivative, needless to say, is a 0. Okay? Difference rule is going to immediately happen here. So now I'm going to break it down as the derivative of x times cosine of y. Okay? Should have used brackets here. And difference rule says now we have two separate derivatives to handle. And the dy dx here, and that's surprisingly easy enough. So in my next step, this is only going to be a dy dx. Okay, and now right here again, what I hope in my viewers is that you will all notice there's a product right here. Okay, so now I'm ready for my next step. So in my next step, taking the derivative of a product, it gives me d, the derivative of the x factor, okay, in respect to x, multiply with cosine of y, leaving cosine of y the same, and I'm going to add, okay, and then here the product rule, because there's a product. So the product rule say, now I'm going to leave the x the same, the first factor the same, and take the derivative, so d of the cosine of y, okay, in respect to x, okay, and then so that is the product rule to take care of the derivative of the first term. The next term, after that subtraction, is simply just the dy dx, and you have seen this action in the earlier problem we've had, and equals 0. Okay, and so feel free to pause the video, but now once I move to the next board, I won't switch back to this anymore. Okay, And so now right from my most recent step right there, then the first term becomes just 1 times the cosine of y. Okay, and then plus, now in my middle term right here, x times, okay, maybe I should swing back. But this term, once again, that term, x times with the derivative of cosine of y. But see, think about the cosine of y. So now, again, y is a function of x. Y is a function of x. So if you're taking scratch work, if we're taking the derivative of cosine of y, okay, y is a function of x. Y is a function of x. But now you're taking the derivative in terms of x, but your function is cosine of y. That means we have an outer function, outside function being cosine. And then inside of this cosine, we have a function y because y represents an entire expression of x inside of it. Okay? So now taking this derivative means we take the derivative in terms of x of that expression. Outside is here, inside is whichever that expression of x inside of y. And so now it's going to be the outside function deals with the cosine, some trig function understanding here. So outside function after taking derivative becomes a negative sine of, we keep the same inside. That's why I'm leaving that y there. Okay? But chain rule again says we're going to multiply with the derivative of the inside. But the inside is only implicitly defined. And so we don't have a choice. We have to leave that as an implicit derivative, dy dx. Okay? And so that is our derivative for that step right there. So now I'm ready to put it in. So now I have x times minus sine of y times dy dx. Okay? And then my next term is a minus dy dx, now equal 0 on the right hand side. Okay? And so feel free to roll back to the earlier steps and see what the earlier step for this particular term was, and now see how I derived at that point. But so now in my next step, okay, I am going, and I don't need to, there's no reason to write that 1 here. So I'm looking at cosine of y, okay, and now it's all products here, so I can say minus x times sine of y times dy dx, okay, and then minus dy dx equal 0. And so now at this point, once again, the work is starting to become as the usual one, how we have seen in the earlier problems. This term here in particular has no dy dx associated with that. Let's bring that to the other side. And then these two terms that I'm about to underline right here, these two terms, they are like terms because they all have in common the common factor dy dx. Okay? And so in my next step, I'm going to go ahead and bring this term cosine of y to the other side. So now I have in my next step x times sine of y, okay, dy dx minus dy dx, and 2 equals negative cosine of y. All right. And then in my next step, now I'm going to factor out the dy dx here, and together with the minus sign. So I can factor out something like this, minus in parentheses x times sine of y plus 1. And then there's a common factor dy dx is being pulled outside. I should have used brackets for that. It's just a little awkward to use 2 levels of parentheses, but indeed they are 2 levels of parentheses. It looks nicer when we write the parentheses and brackets. Equals negative cosine of y. All right, so here we go. We are now so ready to solve for dy dx. So we can now cancel the negative sign on both sides. Okay, cancel that. And then in my next step, I am going to divide both sides by this quantity inside of my brackets here, x times sine of y plus 1. So now my dy dx in the next step here going to give me, so dy dx, okay, is going to equal cosine of y all over, okay, and then I have x times sine of y plus 1. All right, and this is, ladies and gentlemen, our final answer right there. Okay, and so rolling back to my earlier board right there. Then, yes, with a function starting like something like that, and now our final answer in the little space I have remained here, dy dx, okay, it's found to be cosine of y over, okay, minus x sine of y plus 1. Yes, that is our final answer, and we came to the final answer by using implicit differentiation. And we have done quite a few example problems at this point right here. So hopefully you start getting okay, and because I gave the explanation, but throughout all of our example problems, then at any final answer there has always been two variables involved, and that's completely okay. So I just need to clarify that again, again, in case anyone feeling pressure or nervous about having two variables being involved in your final derivative. But that's completely okay now at this point. All right. So now let's get to part D right here. So I am going to spend some time erasing my board here again. All right, so part D of our example. So let's say we have an equation as following. Sine of x times y equals 1/2. The equation looks simple, but it could be dangerous. But no worries, we have already found a way to handle that. And keep in mind again, we got x and y being in equal role. Y can be a variable of x, or x can also be a variable of y. I mean a function of y. But these are all implicit. And so we don't need to solve for one variable in terms of the other ones. We can just take the implicit differentiation. So I am now going to, okay, it's an equation, so I am going to take the derivative equally. Okay, sine of x times y, and equals with, of course, the derivative of the constant term 1/2 on the other hand right there. Okay, and so and at this point I hope I don't have to remind again, but this symbol means it's an operator. We apply the derivative work to this function, to this expression, but that doesn't mean dx times with all that sign thing, or neither it means d dx times with 1/2. It's not, the d dx itself is only an operator. It's indicating what to do. It's an instruction telling the viewers or the students to take the derivative of that expression. Okay, so the right hand side is easier right now. It's a constant, and the function is looking for derivative in terms of x, and so here we are going to take that as a 0. Okay, so derivative of a constant is famously 0, regardless of whichever variable that is. Okay, and so now right here, let's start being cautious a little bit here, and that's the reason why I brought up this example right here. But we already had immediately an outside function, and then inside of that there's all that fancy things, x, y being all in there. So there's outside function be the sine. Maybe let me quickly navigate to the other board and make some to get some empty space right here. So what I have is outside is the sine of something. That's outside. And then inside of the sine function, there's another group of functions. There's x times y in there. Okay, so now right here at this step, at this problem, when we take the derivative here, then we have to stick with the chain rule. And at this point, the whole discussion we've been through so far, the entire lecture here, about implicit differentiation. It's all about applying the chain rule. The chain rule is one of the most fundamental discovery in terms of learning about derivatives right here. So this work right here, taking the derivative, outside function becomes cosine, and to keep the inside the same. That's what chain rule says. We take the derivative of the outside function, and the chain rule also further says we multiply with the derivative of the inside, and now that becomes the derivative of the inside is now, we're going to have to start taking the derivative, the dx of this product. Okay, so I have to tear it down and work on this part a little bit separately right here, and all this here is ready to substitute in our next step. All that there is ready to substitute for this right here. So now the derivative there in the next step becomes cosine of xy, okay, x times y, right, but now multiply with the derivative in respect to x of the product x times y. Okay, so this problem, it is our last problem in example 2, but it happens to be the most challenging one, and I purposely brought it up to let my viewers, my students be experienced, get more experience with these kind of problems right here. All right, so now all that here came out as a consequence of applying the chain rule. So now in the next step, it looks like that factor is done. All we now is to worry about is this here is a product, right? So we're still not quite done with derivative. We have to take the product rule for that product. So now I'm looking at cosine of xy being quite done. Let's leave it there, but now multiply. I'm going to open a square bracket right here. Product rule says we take the derivative of the first factor in respect to x, multiply with the other factor without the derivative, plus, and now the next one here is okay. The next one here is going to be just leaving it the same and multiply with the derivative of the other factor in the product, dy dx, and all that there equals 0. Okay, and so now we are ready for moving into the next space. So in my next board space here, let's look at, all right, so I am now going to have cosine of xy multiply with, okay, and so one more time I'm going to swing back to that earlier board, and this term here, that's the x dx. I mean, it's taking the derivative of the x already explicitly defined as a function of x. So derivative of x is just 1. So 1 times y in my next term, in my next step. Maybe I don't need derivative. I mean, I don't need brackets here anymore. I just need 1 times y is y. Okay. Plus, now back in my earlier board, what I have here, x times the derivative of y in terms of x, but again, y is a function of x. Y is a function of x, but sadly, implicitly, so we don't know what exactly y is in terms of x, so we have to leave that, and we have no choice. So here this is a dy dx. It's the implicit derivative of y as a function of x. All right, and so in that way, this would become x times dy dx. So now in that next term, x times dy dx. Okay, and all that there equals 0. Distribute this out. Okay, and then recombine like terms like that. So now it's going to be y times but by the way, at this step right here, we are officially done with the taking derivative step. So now I'm going to multiply the cosine of xy through each of my term right there. Okay, so y times cosine of xy plus, okay, and x times cosine of xy times dy dx. All right, and all that there equals a 0. And so now I am going to subtract this y to the other side right there. So I'm looking at x times cosine of xy dy dx to equals minus y cosine of xy. Okay, and now we can divide both sides here by x times cosine of xy. So dy dx here is minus y times cosine of xy divided by x times cosine of xy. All right, and so now we can cancel that cosine of xy away. And so our expression finally comes out to be minus y over x. All right, so our final function here, our final derivative is dy dx equals negative y over x. And we are done with that problem again. Okay. All right. And so now, anyone at this point, after seeing me doing so many examples, but they're all dy dx and dy dx, you're starting to wonder. And if you're wondering this question in mind, you're on the right track and you are with the correct understanding. If we can find, in this style of finding derivative, taking the implicit differentiations, if we can find a dy dx, can we find a dx dy? The dx dy. If you were having that thoughts wandering in your mind, you were thinking in the correct way. Okay, and I would love that the fact that any of my students would have that thought in mind before I mention this. Okay, because that means you are understanding and you stay really focused with what's going on. So yes, there will be, we can find the x dy, and let me bring up a couple of examples and for you to gain experience. All right, so let me now erase my example here, all my work here, and so you have to understand at this point, even though in any of my work right here, I might show the long steps and you might have found the shorter steps, that's completely okay. The answer is going to be arriving at the same answer. It's just, I have being in the position of the person teaching here in this video, that I have to, choose the one that laying down, the solution that lay down as many steps as possible so that, as many viewers can follow and understand, and including all of my students right there. But so now back to before I completely erase this example. See, the whole idea I've been saying since the beginning of our lesson here is that this dy dx has a very critical understanding, and so it's fabulous if you can understand that clearly. But it intends that this dy dx symbol intends that the y here in your variable is the function, and the x in your variable, in your dy dx notation here, is the main variable of the equation. Okay, and so in that way, yes, if you were wondering, so what about the x dy? Because now any of these equations, like say the x squared plus y squared equals 4 you have done earlier, this is just simply an equation. Without any specific indication, then which one here can be the function? Any one of them can be the function in terms of the other variable. So if we've been treating y as a function and x as the variable the whole time and only stick with that, this other variable is going to complain. Why you are so unfair? This guy can be the function, why not me? So to be fair, this guy can also be a function and treating the other guy being the variable. So now you can kind of see where I'm going. So now in my example 3, okay, and here once you've had enough experience, I don't have to bring up as many problems anymore in this example 3. But here, yes, what you're waiting for is here. Let's find the x dy. Okay, so let's find the x dy. So I'm not lying, and I did not have a typo. Okay, it's not a mistake. I am asking for the x dy. So let's look at the equation. Okay, now it's just a random choice. My plan here is I'm going to pick any of the problems we have done, and then reinvent over, but this time we're looking for the dx dy. Okay, so How about from the easiest one? The x squared plus y squared equals 4. Okay, the x squared plus y squared equals 4. The whole lecture so far, I've been doing dy dx, and y is a function of x, y is a function of x, all that, okay? But this time we're looking for x as a function of y. So I'm so sorry if I keep making you falling so far into that path saying y is a function of x, y is a function of x. But here we have to turn it upside down. I mean turn it backward. X is a function of y. X is a function of y. X is a function. Y is a variable. X is a function of y. Okay, it sounds like a joke, but trust me, if you're getting for yourself into this habit, you will get the problem done successfully. Okay, so x is a function of y. So now it's an equation. So we can x squared plus y squared. Once again, we can equally take the derivative, but this time be cautious. We twist around the convention, the instruction. We're looking for we're taking the derivative in terms of y. So it's a dy here. Okay? So that means this variable down here, this now, once we're seeing that as a variable, then that means that term now is explicit, and this term here is implicit, but we'll get there. And then right hand side, constant 4, but we're taking the derivative in terms of y. All right. And so now in that way, just all the usual rules applied again. The sum rule, the product rule, the chain rule, they're all going to apply. So right hand side is a 0. The sum rule is going to break that into two separate terms. D, we take the derivative in terms of y of the x squared term plus, and then the derivative in terms of y for the y squared term. Like that. All right. And so now I'm ready for the next step. So see that square term, this term right here. See, I always tend to move on from the easier one to the harder one. So I always, and it's just my style maybe, but I always look for the easier one first. Get it all taken care of so that we can get them out of our way, and then we start taking care of the big guy being the most challenging one. Okay, so we go from the easiest guy and rising up the level like that. So equals 0. That term now, the y squared, this time x is in terms of y. Okay, x is a function in terms of y. Even I get mixed up sometimes. Forgive me on that, but x is a function in terms of y. That means this is already an expression explicitly in terms of y. So why wander around? This thing here is just simply 2y. We don't need the d thingy here, just 2y, because it's already the explicit derivative here. Okay? Now plus that term's there. Now you got to remind yourself, x is a function of y. X is a function of y. That means this is the outside function. Let me make a little scratchy note right here. X is a function of y. That means x squared is the same as think of some outside function being squared. And inside of that square, we have a variable x, which can represent an entire function of y in there that we don't know. We don't know what it is. It's implicitly defined. X here is implicitly defined as a function of y. Okay, so in that way, I shouldn't erase that, a little too rushed. X squared equals, okay, all that big expression. So taking the derivative, okay, in terms of y now, okay, take the derivative. See, that's why I usually don't use this notation too oftenly, because it's easy to mix up which variable that is, but only when we already had a clear indication of some steps before. But now taking the derivative here, we are going to, the chain rule says, take the derivative of the outer function. So that gives us 2x. But now chain rule further says we need to multiply with the derivative of the inside function. So now I'm looking at the dx dy. Okay, so all that here now is a perfect substitution for this term. So now I'm looking at 2x times dx dy. Okay, and so now we are ready for solving for the final dx dy. Okay, and I don't think I need to move on to the other board right here because all that space here is just perfectly enough for our work. This is the non-dx dy term, and this is the only dx dy term. So I'm going to bring that dx dy, the non-dx dy term here to the opposite side. So that means in my next step, I'm producing 2x times dx dy, okay, and all that there equals negative 2y. Okay, and now I'm going to divide both sides by 2x. 2x here as a factor with dx dy. It came out from the chain rule. So now see, I mistake again, but it's okay. Make the same mistake with me and then you're going to learn. Okay, so dx dy equals, and I make the mistake again. Dx dy here equals minus 2y over 2x. It's completely forgivable that we can just keep mixing up because, understandable that we set ourselves so far into using dy dx, so it became a habit. See what I'm saying now? But this here has a whole intention behind the scenes right there. Okay, and we can cancel out the 2. Our final dx dy here. Okay, that's not a mistake. It was just a little scribbling of my writing right there. So minus y over x. All right, so we have found our final implicit derivative from that equation. All right, and so let's try again. Let's try another one. So this time I am going to pick, so in part B, we are going to pick this equation right here, x squared y plus x y cubed equals 4. Okay, but I'm looking for dx dy. And so again, remind yourself, x is a function of y. X is a function in terms of y. So now, so x being intended as a function and y is a variable, but in the end what we have here is an equation. So I am going to write from that equation, x squared y plus x y cubed, I am going to take the derivative but in respect to y as the variable, and equals on the other side, if it was a 4, a constant, but these twos are equal, so taking the derivative would be equal as well. So their two derivatives will be equal. Okay, and so now once again working on the easier side, the constants right here is easy regardless of whatever variable you're finding. Your function is a constant, and so taking the derivative must give you a 0. Okay, and so now the sum rule is breaking in right here because we have a sum of these two terms, and each term involves all that crazy, the xy and xy all over, and we'll get to that. And so now I'm looking at, we need to find a separate derivative in terms of y for x squared y plus a separate derivative in terms of y for xy cubed. And I kind of misplaced my line right here, so I'll rewrite them equal 0. Okay, all right, and so now we are ready for the next step. So this first term, notice how it has a product between the x squared y, okay, and then this next term right here, notice how it has a product between the xy squared right there. So now in my next step, I am going to work out with that part right there. It's a product rule. It's a product. So product rule must apply, right? So now ready into my next step. So the product rule says we have to find the derivative in terms of y of the first factor and multiply with y with our derivative plus, and now we're going to leave the first factor the same and multiply with the derivative in terms of for the function, for that function y in terms of the y variable. Okay, and so that one's easy. That term right there, that factor right there, because it's already explicitly defined. The main derivative, the derivative here is looking for x, is targeting y as the main variable. So here it's already in terms of y, it has already been explicitly defined as a function of y. It's a y to the first power, and so you just simply apply the power rule. So that here becomes just x squared times 1. Okay, and then here x is a function of y. X is a function of y. And so what I have here is x is a function of y. So the x squared there, okay, we can think of that as a squaring being the outside function, and inside of that there's a whole x which is already a function of y inside of that. And so taking that derivative, chain rule says we're going to take the derivative of the outside, so it becomes 2x, and multiply with the derivative of the inside. And remember, we are defining x implicitly as a function of y. So when we come to the derivative, it has to be again an implicit derivative. So it's a dx dy here. Okay, and so now these two terms immediately becomes so 2x for that, 2x times dx dy for that terms and times y, and then plus x squared plus 1. That's how these two terms become. But now I'm not done really. All of that here takes care of my derivative of the first term. And now I'm going to underline the next term here. Okay, the next term here has a product again of the two factors x and the y cubed like that. All right, so in my next step, add, and so the product rule say I'm going to take the derivative in respect to y of the function x, multiply with y cubed, okay, plus, now I'm going to leave the first one here the same, okay, and multiply with the derivative of y cubed in terms of y, and all that there equals a 0. Okay, so my writing is getting a little squeezy here, but this 0 is the right hand side, and all these two terms are here. Once again, x is an implicit function of y right there. So dx dy, we didn't know what x is as a function of y. We only know that it's defined implicitly, and so we have no choice rather than just leaving that as an implicit derivative. So it's dx dy here, that comes down for this, multiply with y cubed, and then all that there is now plus x times, so this is taking the derivative but in respect to the y variable, and our expression has already been in terms of y, so this is explicit here. We're going to take the derivative, so it's just 3y squared, so x times 3y squared, and all that there equals 0. All right, so now let's clean up the terms right here. So in my next step, it's just a matter of rewriting the term. First term becomes 2xy and see, I already had a mistake right here. I should have written in my earlier step. That should have been dx dy right there. And I wrote dx. Okay, so this is 2xy dx dy plus, and here it's just simply x squared, okay, plus, and that term right there is a y cubed dx dy plus, now I'm looking at 3xy squared equals 0. Okay, and so now after seeing quite a few examples prior to this one right here, then we can go ahead and combine like terms. These are the non-dx dy terms right here. Bring them to the opposite side. And then in the meanwhile, I'm going to speed up the process a little bit. I'm going to combine these two like terms. They are like terms in a sense that they have the common factor dx dy. So I'm going to be looking at xy plus y cubed, because these two terms right here, after factoring out the dx dy. Dx dy, okay, so 2xy plus y cubed times dx dy equals all these non-dx dy terms. I'm going to bring them to the opposite side. So now it's minus x squared minus 3xy squared. Okay, and so now we are ready to solve for this final dx dy over here. So it's just a matter of dividing that away, that expression 2xy plus y cubed right here. So dx dy equals to minus x squared minus 3xy squared, and we're dividing that by 2xy plus y cubed. Okay, and this is our final answer. Or maybe let me go back to the other board and to write down the final answer there on my other board right there. Okay. All right, so final answer for this problem is here. We found dx dy for this problem. Dx dy here is going to be minus x squared minus 3xy squared, okay, all over 2xy plus y cubed, and that's our final answer. Okay, and once again, of course, we have gone a long way, so forgive me if I made any typo errors that came out from typos. All right, but that's how we have been finding implicit differentiation. I mean, applying the technique of implicit differentiation. It's a technique so that we can take derivative implicitly right from an equation where any of our function can be implicitly defined in terms of as a function in terms of the other function. All right, and now I'm going to take a moment to erase my board, and I'm going to complete our lesson here with another example where we're going to find tangent line again. We did one in the beginning, but I'm going to create another one where we're all going to, find it all from scratch right here. All right, and so now finding tangent line is the best place where we apply our skills in finding derivative. So when it comes to this, I can leave the derivative steps for you to take. Okay, and then I'll just help in with the other steps to remind you the general structure for finding any equation of any tangent line. So example 4, how's that? All right, so here in my example, find the equation. Okay, find the equation of the tangent line. To the equation. So x squared over 16 plus y squared over 9 equals 2. Okay, so find the equation of the tangent line. All right, the tangent line to this graph right here, and the graph came out from this equation at and the complete point. So here we have to give the complete point 4, 3. So this is our tangent point right here, and this tangent point exists on the graph, whatever the graph of that equation, and we want to find the equation of the tangent line. All right, and so take a moment to think of the plan right here as I'm erasing the board. And so now, to begin any tangent line problem, the first thing is to get the slope, because any line y equals mx plus b, and our particular line here is a special line, it's a tangent line, so I always use that subscript, capital T right there. All right, and so now to find the subscript, capital T, your first step right here is to find the derivative, okay, the dy dx. And now we're getting back to just the usual dy dx. Even though, as a matter of fact, it shouldn't matter too much, okay? At this point, being able to find derivative implicitly, you should, I mean, the x dy or dy dx is pretty much all going to get it work. But so here's the thing. I mean, if you go with dx dy, it's going to be a little trickier, because you see, your final equation is written as a function in terms of x. And so that's why your derivative here has to be a dx, has to be a dy dx. If you were the same, but see, equation is an equation. The same tangent line can also be written as some x equals a different slope, mt y plus b right here. If you are attempting to write your equation in the form of x as a function of y, then you can start out by finding the dx dy, okay? And that's my intention for this kind of problem right here. Because like I said, if any of you follow really closely with my lecture up to this point, why does it have to be dy dx, where we can also find it as a dx dy? But, yes, you are correct, but you have to know that you find this for when your equation is being in this form. If you decide to go with this form, x equals mty plus b, then you're going to start out by finding the dx dy, and that's the whole point. So, but let's stay with things that everyone has been comfortable with. This one here, including me, I'm more comfortable with this form, okay? And so now dy dx, now I can leave that for you to use your skill that you have learned so far in finding implicit differentiation, right? Get me the derivative for that function right there, for that equation, okay? All right, so hopefully at this point you've had some thoughts about that. And so I can throw in one step before that, but your successful taking implicit differentiation at this point is going to be, it's a 2x over 16 plus, and then 2y over 9, but times a dy dx, right? And equals a 0, okay? And this is a 9, by the way, okay? And so in that way, our final dy dx here must be going to be, it's going to be a minus 2x over 16 divided by a 2y over 9 right there. And in other words, okay? And so our final dy dx here is a minus 9x over 16y algebraically, okay? Minus 9x over 16y. And so in that way, now the slope of the tangent line is going to be whatever we have found for our general implicit differentiation, but evaluated at the given point 4, 3. This is our given tangent line, okay? And so once again, let me quickly bring up the picture so that you can see the reason why tangent point must be given as a complete point right there. So for our graph right here, x squared over 16 plus y squared over 9 equals 2. It's an ellipse. Okay, so the graph for that is an ellipse. And so being an ellipse right here, so now with the value being 4, 3, or maybe let me quickly generate that point right there. 4, 3, it's that point right there. Okay, And then so with this point right here, then it's going to be, we're going to have, see, if we simply just give x equals 4, then we are going to end up with 2 different y values, and consequently we will have 2 different tangent lines. And so to specifically indicate what tangent line we're looking at, we have to give the complete tangent point with x and y coordinates, x and y values are being given. All right, so that's a quick, some quick developments about the problem. But now let's get ready for the problem right here. So back to my slope that I'm halfway found, that I'm halfway on my way finding it. Then the dy dx here substituted in the pair of values 4, 3. So that means we have 9 times minus 9 times x value is 4 divided by 16 times y, but y here is 3. Okay, and so our final value for this is going to be now some algebraic cancellations for the algebra can come out. And so we're looking at minus 3 over 4, which is, you can think of that. I recommend keeping a fraction like that, or you can think of that as a negative 0.75. So that's your slope, and I don't even think I need to put this in a box right there, because it's not even our final answer. All right, so we got the slope of the tangent line. So the line has to look like this. Y equals the equation of a tangent line must be y equals minus 3/4 x plus b. Okay, and so it's a halfway done equation. So now when it comes to the tangent point, we already had a tangent point given. I just want to briefly remind that for anyone as a general step, as a general picture of finding the equation of a tangent line, we always need to indicate what tangent point we're looking at. That's the point being 4, 3. Okay, and so now for our equation, we are looking at, I can just use my, and you got your own control over this to have your own way of finding the y-intercept. So I'll go with 3 equals negative 3/4 times 4 for x plus b. And then from there we can solve for our value b to equals, so the 4 cancel with that, so b equals 6. So our final tangent line here, equation of a tangent line is y equals negative 3/4 x plus 6. All right, so that's our equation of a tangent line. So now I can go ahead and show you that on the picture here. Okay, that's still not the correct line yet, so let me hide it away. All right, so the picture is here. So now let me bring up the actual graph. All right, so now you see this is our tangent point being right at 4, 3, and this line right here is that line being the equation for that is, I typed it in decimal, and I typed in negative 3 over 4x plus 6 right here, and I got this line in green, and that does look like being tangent to this ellipse at the point of 4, 3.